Okay, good morning, students. Welcome, everybody. So it's Adam again. Okay. So let's start this meeting, this lesson. Today we have two lessons. First one is continuation transient analysis, the second part of this topic, and after that we are talking about the parsers. So I have a hope that you are wake up, and it is a good idea to drink some coffee for before, or maybe in this time, because it is quite heavy, quite heavy lecture, and after that it's more it is less heavy. It is light lecture about parsers. Okay, so let's start. I have hope that you hear me good. And so at the beginning we are reminding about the previous lecture. So at the previous lecture we are applying the Laplace transform. We convert the differential equations in time domain to the algebraic equation in S domain. So we solved equations in S domain, and we converted the results back into the time domain. And I have a hope that you know about the Laplace transform definition. So it is here, and we also know the Laplace transform pairs that can be used to convert back and forth between the time and frequency domain. We also know the definitions for Riemann integration to back again to time domain, but of course it is not convenient to use for us. Okay, and the Laplace transform properties were useful in performing the Laplace transform and in inverse. I showed you a table with 10 properties of Laplace transformation, and the most powerful is partial fraction expansion of function in S domain. To convert the function to time domain, we had three cases of partial fraction expansion, and today we are continue in the electrical circuit with this conversation, and at the end I'll show you the convolution of two functions in time domain, and I show you the relation between time domain and S domain. Also I showed you the example with in LabVIEW and PSpice that I use the convolution to solve the circuit. Okay, so let's start. At the beginning, we consider the network with assumption steady state prior to t equal 0. So we just should find the current function for t more than 0. Okay, so we have here the schematic, and here we have the switch. And at this moment, switch before this time was closed, and exactly at this time t equals 0 is open. So we can calculate the state before this action. So before this action, we know that we change the capacitor as a break for the constant current and constant voltage in the DC circuits. So it is very simple to calculate this circuit, and we have here the voltage source, 12 voltage, and we have also 2 resistors. So when we divide this voltage by this sum of resistors, we obtain the current 4 amperes, and the voltage at this resistor, and this is the same voltage across the capacitor, is equal to just 4 voltage. Okay, and we can apply the Kirchhoff voltage law equations for this network for time more than 0, and so the time for this time we have this circuit only. Because the resistor is unplugged from this circuit, so now we have this voltage here, and now this is this current, and this voltage is voltage across this resistor, and this part is describes the voltage across this inductor, and this is connected with capacitors. So with the state before, so this is the part connected with the voltage before, change the switch and the previous situation. Okay, so we can transform this expression to S domain. So we know about firstly we know about additions of subtractions to functions and sum of functions, and we also use the property number 6, which is connected with differentiation, and property number 9. It is connected with the integrations, and now we just obtain this is the just 12 by S, because the unit functions, and here we have the transformation. We know that differentiation is in time domain. It means that in S domain we have to make a multiplication by S, and this is the connected. This is the current connected with steady state before, and some results connected with capacitors. voltage across the capacitors. And after some calculations, we must rearrange these parts of equations, and as a result, we make the partial fraction of these equations. And when we have it, we can when we have this one, we can calculate the coefficient K1, and we have here the complex number, and as a result, we obtain the current in our circuit. Okay, and so we can also calculate, because it is the current as a function of t. So we return to the t domain, and for example, we can put instead of t the 0, and at the 0 we obtain from these equations, of course, the same value at for this this value, and this value is the same. Okay, and now I make the simulation of this circuit, and we can see that at this moment, and for t equals 0. So in the SPICE, I use the time equal 10 milliseconds, because it is not possible to use just 0. So it's not afraid about it. It is not important. So if I can, I put here 0. So but it is impossible in this program. Okay, and here I draw the voltage across the capacitor and the current. So the current starts at 4, and also the voltage starts at 4 voltage, and current goes to the 0 after, for example, 5 seconds. Now, of course, we know that for capacitor is the break for DC, and this current is connected with this, and voltage across the capacitor goes to the voltage source voltage, and 12 voltage here. Okay, and this oscillations is connected with this factor cosinus at these equations. Okay, and now we are talking about problem solving strategy in electric circuits. So firstly, we assume that the circuit has reached a steady state before a switch is moved. So it is connected with for example, with the circuit which was presented before. And firstly, we should draw the circuit valid for t minus 0, and we have to replacing capacitors with open circuit and inductors with short circuits. And after that, we solve for the initial conditions. Voltage across capacitors and currents flowing through the capacitors. So we must remember that the voltage before and just before and just after is the same, and the same situation is for the current. It is from commutation law that this law say us that the current on voltage is it is not possible to in real circuit, and not possible to change immediately from one to another value. Of course, maybe you remember the unit functions and delta functions, but this is only for mathematics point of view. This is the change is infinity at the moment, but in real circuit is not possible. Okay, and the second, draw the circuit valid for t more than 0 and use the circuit analysis technique to determine the differential or integral differential equations that describe the behavior of the circuit. And the third, convert these equations to the algebraic equations using Laplace transform. Fourth, solve these algebraic equations for variable of interest. Your results will be ratio of polynomial in the complex variable of S. And at the end, perform the inverse Laplace transform for solve for the circuit response in time domain. So this is the prescriptions how we can solve the circuits. Okay, and now we try to compare calculation in time domain and just only in the time domain using differential equations and using the S domain, Laplace transformation. So we have very simple circuit. We have just the voltage source, resistors, and inductors, and so now we can draw the equation. We can write the equations for this circuit. So the voltage from source, it is the sum of voltage across the inductor and across the resistor. And we have the here we can write the current as a function of time in this circuit as a form of complementary and particular part of this current, and we solve this, separate the first and the second and the second part of this. Okay, firstly, the complementary differential equation is maybe it's known for this because I know that you use the differential equations now, and maybe it's simply maybe more simply than for me at this time, because I had the differential equations some 10 years ago. But okay, so we have here the first equations in the complementary differential equations. We put instead of this source 0, and so after some calculations, we just should move for this side, this component connected with the R, and after that we have on the left we have DIC, and on the right we have the DT. So we must separate this part, and so when we make this separation, we can both sides integrate. After integration, we obtain such results connected with this, and we have also the key one. It is the constant, and now we can use the trick for this, because here I have just constants, And I know that I can use another constant as a natural logarithm of another constant key C. It is more convenient because I can move from this side to this side, this part connected with the constant, and as a result, we obtain that we have the solutions for complementary differential equations as constants e up to this factor. Okay, but it is only the one part, and the particular solution if of the same form as a forcing function as Vs from t. So I put for this the number 1, and here I just have only this part. And when we substituting into the original differential equations this one, we obtain that the differentiation from constant is equal 0, and here on the left side we have just 1, and from this side we have R and constant key P. So we can calculate these constants from this, and so the final solution is the sum of this one and this one current, and now we can find the constant key C and key P. So we can solve this, and maybe I go to the final results. As a final results, we obtain just the function of t current as a function of t. So I use here the milliamperes, so it is the value more than 1 in here and here. So you must notice that this equation is with milliamperes. Okay, so this is the first solution of this circle using only the differential equations and without any changes to S domain and back again. Okay, but we know that we have another method, and the different approach for the same problem is Laplace transform. And I think that this man should tell that he preferred the second method. Okay, so try to use the Laplace transformation for the same circuit. Okay, the circuit is the same, and firstly we try to convert from time domain into the S domain, and the Laplace transformation of this is equal. The voltage, it is the sum of voltage across the inductor and across the resistor. Later, I show you the relation between transformation and elements. Now, just trust me that this is the inductority be multiplied by this one, and it is the voltage across the inductor, and just R multiplied by I or from S, it is the voltage across this one. Okay, and so we notice that because we don't know about the initial value, so we can assume that the current at the beginning is equal 0. So this is equal 0, and we have just equations from this one. And now we can try to calculate from this the current, because for R is interesting the current and as a function of time. Okay, and so we just arrange the components and we obtain the current as such result. But it is not good results from the partial fraction point of view. So, of course, we find the function of time of current using the inverse Laplace transformation. But first, we can express I from S as a sum of partial products, and so we must rearrange this one, and because it is not convenient when we have here S and L. Maybe you remember that in the transformation which I show you, there is always S without any factors. We just have S in, for example, in the denominator or in the numerator, and the S square, but without any coefficients here. So we must use these calculations to obtain sum of partial product, for example, as here. Okay, so of course, as with factor here, it is a good idea, but I mean about this one with the brackets, and so because it is only the coefficients. But when we have the S with something plus something, it is not good from the partial product. Okay, and so from this one we can just write the results, and as results we obtain. The first one is connected with the constant. It is just 1 by R, and this one is also constant, but this one it is connected with time, with this factor e up to some factor. It means this 1 by S plus constant. Okay, and as a result, we obtain the same value when we put instead of when we substitute R and L from these equations, we obtain this value. Okay, and since the voltage, we must remember that since the voltage current relationship for resistor, capacitors, and inductors involve only constant derivative integrals, we can represent and solve any circuit in S domain. Okay, now I show you how we can represent the circuit's elements model in S domain. Okay, so at the left we have the time domain, on the right S domain, and first the resistors. We know that the equations for resistors, just the voltage across the resistor, it is current multiplied by just the coefficients R. And this is the schematic. Here we use the Laplace transformation for both sides. As a result, we obtain voltage in S domain is equal transformation of current and multiplied by R. And this is the same resistors, of course, and for resistor it is the simple, because we just instead of I from T, we wrote the big I from S, and the same from the voltage. Okay, this simplest elements, and the second, and this is the capacitor, and from the capacitor we have the complet of double equations describes the capacitors for voltage and for current. And for voltage, we use the integrations for current differentiations. And now we have some circuits and this capacitor here. Here is the current. And in the S domain, we just use the property. We know that the integration in the time domain means it is we just use the 1 by S in S domain, and we also know about the constants, because we have the constant in time domain, and the constant is the same by S. And this is for the current from differentiation, we multiplication by S with in time in S domain. Okay, so we can represent the first one as a capacitor with series in voltage source, and for this equation we use such circuit when we put the parallel source connected with this one. Okay, and for the inductors, inductor in time domain is described by these equations. It's a similar situation to the capacitors, and in this domain, S domain, we have also the complet of equations, but we just take very similar equations, but we have also take to focus in the direction of current, and in this original circle, because it is connected with direction of the sources. So you may pay attention for this. Okay, and coupled inductors, and so when we know the questions for inductors, maybe it's not difficult to guess for this, and the schematic, and in the S domain it is more complicated, but it is just the first and second is connected with R1, and this rest of this equation is connected with the coupling. And this schema we can replace by this schema in S domain. Okay, and also we have the sources, the voltage source and current sources. And so in the S domain, it is just the transformation. For control source, we have, for example, we have here the voltage controlled by current source. So it is also the transformation, and this multiplication by these coefficients. It is similar to resistors. And important information I told you, but it's very important that the direction of the current sources and polarity of voltage, so is the transformer network results from the initial conditions. So if the polarity of the initial voltage or direction of the initial current is reversed, it is the same in the S domain. So we must remember about it. Okay, and now we can try to find the output voltage in both S and time domain. We have such circuit. We know about the function of the source current, and we have resistor capacitors here. Okay, and now because we don't know about the steady state before, we can assume that the voltage here is equal 0 at the start. Okay, so we just transform this function into S domain. So we have here the coefficients e up to minus t. It is represented by s plus 1 in the denominator. This one is represented by this 3 in the nominator. And here we have the just resistor, the same value. And instead of capacitors, we use 1 by SC. And when I put 25 microfarads, I obtain this value. Okay, and now we can solve using the knowing methods for circuit analysis, but in the S domain. And so we have here just current source, and we should calculate the voltage here, and this voltage here, it is just current multiplied by this value connected together, resistor and capacitor. We know that resistor and capacitor is connected parallel in this circuit. So as results, we know the impedance for this is it is the resistance by this reactance, and multiplication in the denominator we have the sum of this. It is the same. For example, when we put here the resistor, we just instead of 1 by CS, we use the second resistor. So we have the equations for voltage connected with the IS. And now I just put the results from this, and this one is connected with capacitors, and capacitors here we have the 1 by C, and here we have the S, and fourth is connected with this this part, and this one I use 0.003 because this current is described with milliamperes, and when I calculate, I obtain such value. Of course, this value is written here, and it is nice equations, but not from point of view transformation to the time domain. And now we can use the knowing method and expanding this output from S into partial fraction, yes, and we can use the first one, the simple pores methods for this, and as a result we have the two parts from these equations, and so we can just transform to the time domain, and as a result we obtain this part connected with this. So we have to here just E up to minus t, and this is connected with this part of equations, and this constants is before brackets. And of course, it is there is not one idea how I can transform this one into the partial fraction. It is not simple. Of course, it is this example is from this example has also the good numbers for this. It is not. We cannot doing for every values. It's not simple at all cases. Okay, and so this is the voltage of the output, and so now we can use the analysis techniques in S domain. For example, mesh analysis. You calculate many examples using the mesh analysis at exercises. So now let's us write the mesh equations in S domain for such network. Okay, so we have here the two sources, voltage sources, and yes, two resistors, two capacitors, and two inductors. So we draw some directions for the current here and the voltage across the capacitors. So when we assumed here the current at this direction, we obtained the direction of voltage at these capacitors. And for example, this current goes from this direction, and it is connected with this direction of the voltage across capacitors here. Okay, so we instead of this one, we transform all of this. So we have just the transform the voltage sources and resistors, capacitors, and we must remember about the sources connected with capacitors and connected with the inductors. And of course, we should take to account the direction of the currents. As a result, we obtain such circuit. And now we can write using the mesh analysis, mesh equations. Firstly, connected with the first loop, and we have the second loop here. And direction is according to the clock direction. And firstly, we have the from the first loop. We have the parts connected with this first current R1, and this is connected with these capacitors and inductors, and the common part we have here always with the minus, and common part this loop and this loop is here. It is just 1 by CS2 plus SL1, and on the right side of equations we have the voltage sources. Of course, it is when we are planning to use the mesh analysis, we don't substitute instead of capacitors the circuit connected with capacitors and current source, because it is not convenient in mesh analysis. For mesh analysis, we use the representation in S domain elements with voltage source. So here we have the voltage source connected with the first loop. We have here the fourth source. So we take into account the direction, and we obtain the first and this one we have the plus, and the rest minus. And the same we can write for the second loop, and this is the impedance connected with the second loop, and impedance, common impedance, and this is the same. Okay, and we can also use the node equations in S domain, and for node equations it is convenient use the current sources. So we can put, instead, for example, this inductor, I put here the inductor, and representation in S domain this inductor, and the current source, and the same for another parts of this one. And as a result, we use here, instead of impedance, we use admittance in nodal analysis. And from this node we have here the two nodes, and from this node, admittance connected with this node is consists from 4 elements, here, and here. And between the first and the second node, we have the capacitors C1 and inductor L2. And on the right side, we summarize the current connected with this first node. And the same we can use the same for the second node, and we know that this one and this one is the same. Okay, so maybe at this moment we make a short break. I should save the throat, because it is the long time today for the lecture, and so we start about 10:15. To the second part of this lecture after break. Okay, so now we try to use knowing methods to analyze the circuit in S domain. I know that you are masters in analysis in the circuit. Grzegorz said me about it. So this is very similar using this method in the S domain. Okay, so let's determine the output voltage V0 in the time domain using first nodal analysis, mesh analysis, superposition, source exchange, and Thevenin theorem and Norton theorem. So we have here the six methods for this, and we must put the attention that the results should be the same in all cases. Okay, so first nodal analysis. Nodal analysis for this schematic. So we can put here, instead of capacitors and inductors, another value, because we have the one here. It represents 1 farad. It represents just by 1 by S, and S represents the inductors, and we have the sources, and because it is the constant value, we have just 4 by s and 12 by s in this situation. And now we have one node here. We can assume that we have one node, and from this this node we know the reactance connected with this with the here is the reactance connected with the inductor, and in the capacitors and resistors in the series. So it is the one by impedance, it is admittance connected with to this node, and at the right side we have just current and current connected with this source, and current connected with this source. Okay, and maybe you noticed that in this analysis I omit these resistors, because these resistors it have not any influence in this circuit, because it is series connected with current source. So it can change the current, can change anything. Okay, so now I put instead of letters the numbers, and as results I obtain the voltage and this at this point. And when I have the voltage at this point, I just use the voltage divider for this one, and so we have the relation between voltage V1 and V0 at this, and applying the voltage divider here, I obtain the final result, of course, in the S domain. Now we calculate the output in S domain, and after this 6th method we change to the time domain. Okay, so for mesh analysis we have the 2 loops here, and for the right loop it is for the right loop the first equations. We have here the voltage source and the voltage across the inductor is given by the differentiation of 2 currents and multiplication by this S, and voltage across this capacitor, and the rest across the resistor, and of course it is equal 0. And for left loop it is a very good situation, because we have here only the source, the current source. So the current, this loop current I1 is just equal the source current. Okay, and when I substitute this value to the first equations, I obtain such value. And when I have the this current, so the voltage output is equal just this current multiplied by this resistor. So I obtain the same result in the first and the second method. So up to now it is good. Okay, third, it is the superposition method. You know about it, that we in the superposition method we just write the not one by we divide one circuit into the another circuit when we have only the one source. And so because in this case we have the two sources, we should draw two circuits. First, with the current sources and the first source, and the second source we change the source into the short for the voltage source and break for the current source. So because we have in this part the voltage source, I use the short for this. And the second, from this circuit we calculate the VO prime, and we have the second circuit when we calculate VOBs, but in this circuit we have the voltage source, and instead of current source I have the break. Okay, and now from the first for the first circuit. For the first circuit, we are applying the current divider, and in the denominator I put all impedance, and when I want to calculate the current which flow in this part of the circuit, in the denominator I should put just S, and the impedance from this part of circuit. And so this is connected with the current source. This is current source and current divider, and as a current divider I have the current which flow in this part, and when I multiply it by this resistor I obtain the V0 prime, and this is the results for this voltage. And the second, we have the very simple circuits here. So we have just the voltage source and three elements. So we use the voltage divider for this, and so we have the voltage, and here is the sum of impedance in the denominator, and in denominator I put this resistance, and we have the VOBs. Now I should summarize the voltage from the first and from the second circuit. And when I do it, I obtain knowing results from the VO from S. Okay, and now fourth method, source exchange method. So it is the original circuit, and for instance, in this circuit, it is a good idea to replace this source by current source. And here we have such circuit with two current source, and this current source I represent by this voltage I represent by this, and by these elements. So I cannot change only the source, but the voltage source connected with the series elements. So this part is replaced by this part. But here I should divide also by this elements. Okay, and so we have this information here, and now I have two sources. I omit this resistor because it hasn't influence in this circuit. Okay, so we just add the first one and the second one current, and applying the current divider here, and multiply by the value of resistors here, and obtain the voltage across this resistor, so voltage out. Okay, and also we obtain the same results. And now two methods and very good methods. I very like the Thevenin method from the circuit analysis, and from Thevenin method we have the original circuit, and when we want to use the Thevenin method, first we cut the part of circuit when we want to calculate the voltage, and after that we have open circuit for this, because I removed from this resistor, and now we can calculate the open circuit voltage for this, and for this open circuit, the voltage at this termination is equal to this voltage plus voltage across the inductor. And when we calculate, because in this currents flow only in this circuit, so we have here the voltage. We can calculate that the voltage across this inductor is just 4 by S, because it's the source value, and S multiplication by S. So as a result, I obtain such value. Of course, because here we have the current equals 0, so we haven't any voltage across the capacitor. Okay, so we have the open circuit voltage, and the second value which we should calculate in the Thevenin method is Thevenin equivalent impedance. So we calculate the impedance from this port, looking at this port, and from in this calculation we change. We substitute, instead of current source, the break, and instead of voltage source, the short. And now the impedance consists only from impedance connected with capacitors and inductors. As a result, we obtain such value. And now we have the open circuit voltage and Thevenin equivalent impedance, so we can draw the substitute circuit. And so this is the circuit. We have the open circuit voltage here, and in the series of equivalent impedance. And in this circuit, I have to connect the part which I removed at the beginning. So I removed only the resistors, so I put here the resistors, and now I calculate the voltage across in this circuit. From this circuit, we just use the voltage divider. We have the voltage source, and now it is the impedance whole circuit, and this resistance, and at the end we obtain the same result of the voltage output. Okay, and for Norton method, Norton method is very similar, but instead of calculate open circuit voltage, we calculate the current, short current here. And so we are interested in this current, so we cut these elements and just make a short here. And the short circuit current in this one is equal this current plus currents connected with this source. For example, here it is a good idea to change this current into the current source. Okay, so we have the current here, and as secondly, we can calculate the impedance, and for the same method. So we have here the ports and impedance from this port. It is only in this case only S, because it is break for this source and short for this. And as a result, we have the current source and Norton equivalent impedance in parallel. So it is the different approach compared to the Thevenin method. And here I have the rest of the circuit, original circuit. And as a result, we can use here the current divider, and we calculate the current here. And when we multiply this current by this value, we obtain the voltage output. And it is also the same value. And now, at the end, we should transfer to time domain these results. So you know about this value. We obtain 6 times this value. So finally, we should transform it to the time domain. So because we have the square here, we can try use the such functions for transform for the partial fraction. And now, firstly, we calculate the coefficients connected with the highest number of power, and we obtain the 16. And after that, we must do the differentiation for this and calculate the key 1, 2. And as a result, we obtain such partial fraction equations for V0 in S domain. And now it is simple to change domain into the time domain, and on the time domain we obtain such value and the output. Okay, so now short example circuits with controlled source. Okay, so we have here the current source, some inductors, capacitors, 2 resistors, switch, and here is the current source controlled by current which flows here by this resistor. Okay, so we have some data for this circuit. It is we have here the current function and value for the parts, and this is the coefficients alpha connected with this source. So when, for example, when here we have 1 ampere, this current value is equal 1 by 5. So here we have 5 amperes, and we have to calculate voltage across the resistor R2. Okay, so another data is connected with the initial conditions. So we know about the voltage across the capacitors and currents flow for the inductors. And so now we write this this circuit when we open the switch. Okay, and now we calculate, transform the current source into the S domain. So we know that sinus it is equal 1 by S squared plus 1 plus omega square, but omega here is equal 1. So we have just these results. And now we can use the nodal analysis for this, and we have two nodes here, and the admutation connected with the first one, and admutation connected with the second one, and currents connected with first one is equal just IS, and current connected with the second one, with the second node, it is connected with this source, controlled source. So we put here for in the same way the current source, and instead of this current, we put just voltage across this V1 by R1, because we know that this current controls this source. Okay, and now we have the writing these equations, and now we can use the matrix system for this. That because it is very convenient using nodal analysis in the matrix form, and it gives simple calculation. So here we have the first component and the second. It's clear, I think. And now I put because the source, current source, controlled current source is controlled by voltage V1. So I moved from this component from the right part to the left part, because I have here the relation connected with V1. So here alpha by R1 is appeared from this in this matrix, of course with minus, because I moved from this side to this side. Okay, and so we have the matrix, and now we can calculate substitute the values for this, and now we can try to calculate the determined main matrix for this. So just knowing method for that, and now because I want to know V2, so instead of this this column, I substitute this value. Okay, and from for this one, I obtain the determined connected with changed matrix, and so I have the first determined and the second determined, and the value of V2 from the Cramer's rule is knowing that when I divide this determined by this main matrix determined, I obtain the V from S value. So, and as a result, I have here the partial fraction of these equations, and now it looks good, but we have some changes here. Maybe you see where, but even now I show you that there is the one small difference in these equations compared to equations which we talking about up to now. Okay, and maybe you don't notice it, but I show you in the red rectangular. But it is very strange when we obtain in the denominator s minus something. Minus something, because when we remember the pairs of transformation, we have here always the plus connected with s plus something in the denominator, because when we transform such element to the time domain, we obtain such result that when we have here plus, we obtain minus in the time domain. But here we have the plus with the power of e here. So this is not good, because this value of voltage grows and grows with the times. Okay, and so I show you the simulation with this case, and okay, so we have here in this we have the current source. So we know about the amplitude. It's about 20 amperes, and it is the voltage on the output. And so I calculate this voltage for at the moment 2 seconds. 2 seconds after the switch was open, and I obtained the results 125 voltage, and you see that for the simulation I obtained the same value. So it is true, and that sometimes we can make the circuits when the voltage is unpredictable. Of course, in this circuit, in practical point of view, there are some limitations for example, for the currents of the controlled source here, but it is possible. So it is possible, and when we have controlled voltage, sometimes the current value or voltage value is unpredictable. So such like this case, of course, after for example 10 seconds, it is a strange value here, and you can calculate using this one, because it is this growing not going fast, it's going down, and this is the periodic function. So it is it is only connected with this going is connected with this part. Okay, and now I try to talk to you about the transfer function. Transfer function in the circuit analysis is the ratio of some output variable to some input variable. So we have the relation between output and the input in S domain, and maybe not I told about it previously, maybe not in the direct way, but now more formalized. Okay, so for example, when we have both variables voltage, we obtain the voltage gain. Because we have the relation between voltage and voltage, both variables are current, we obtain current gain. One variable is voltage and another is current, so transfer function becomes the transfer impedance or admittance. It depends which is the on the output and on the input. Important information is to obtain a transfer function. To obtain transfer function, all initial conditions are set equal to 0. So transfer function is for initial conditions equal 0. And let's assume that the input-output relationship for linear circuit. So we have the differential equations for connected with output with letter O and some parts connected with the input with letter E, and because all the initial conditions are 0, we transform of equations into S domain. So as a result, we obtain the polynomial ratio of two polynomials connected with the input and output. Okay, and so we know the relation between input and the output is connected. We use the transfer functions. Okay, and of course, when we have the delta on the input, delta function on the input, so the transformation of delta is equal 1. So the impulse response is equal to the inverse Laplace transform of transform functions. So the impulse response it is just inverse transform of transfer function. Okay, and I showed you 1 week ago. We had examples with the digital scope, but we used the unit function instead of delta because we cannot produce this delta in practice. Okay, and so now we can try to analyze the equations connected with the transfer functions, and we make some two cases. We consider two cases. The first order network, when we have the transfer function as this one, and we have here the three constants, and we have S with first power in the denominator, and so if only a single storage element is present, single storage element, it means it is the capacitor or inductors. The natural response of the network or initial conditions is always of the form. So this is the solution for this. We have such some constants here, and here we have the tau. And tau is the constant, time constant of the network. It's called time constant of the network. And this coefficient is connected with initial value of ft. Okay, so you can consider the first order network. We have one storage element here, and we can writing the equations for this using the voltage divider. And now we know about the voltage and the input in the output, and when we divide, we obtain the transfer function. So of course the E from S is disappear in this situation, and on the results we obtain the convenient equations to transfer into the time domain, and here we see the tau. Now we have the the tau is equal RC. This is the time constant, and when we transform this to the time domain, we obtain such results. So this it is similar to this one. Okay, and more interesting is the second order network. In the second order network, we see that in the denominator we have additional elements connected with the S, and in the denominator is it is also some elements connected with S square. So the natural response of it is the second order network, because we have the here is the number 2. So it's determine the which order we have. So the natural response of second order network is controlled by roots of characteristic equations. So we remember with denominator we have zeros, and we have poles in the denominator, such functions. So we know that it is controlled, the response is controlled by roots of characteristic equations. So we have such equations where this letter is zeta. Zeta is the damping ratio, and omega 0 is the undamped natural frequency. So we have such characteristic equations for this, and we know that those two parameters, so because it is only two, zeta and omega, control the response, and therefore the network is one of the forms. So we can obtain one of three forms. And firstly, we have when the zeta is more than 1, we obtain overdamped network. And overdamped network, so we calculate the roots for these equations, characteristic equations, and we obtain such value. And from this in these situations we obtain such a response of our system. And when zeta is less than 1, we obtain the underdamped network. And for underdamped network, you notice that the first is the same, roots of characteristic equations, but here we have the J form, so we have here the imaginary part. Okay, and from this, in these situations, we obtain such response. When we see we have such oscillations in this case, because we have the period functions here, and there is the case between the first and the second when zeta is equal 1. So we have the critically damped network, and from this, of course, it is simple to obtain. When we substitute here the 1, we have 0 here, and it is just minus omega. And from this, the response is very simple, and consists from this part, and from this part. This part is it consists only with this one and constants, and here we have also the t. Okay, and so this is the what is mean. when we have overdamped damped network, we start from some value and go the response go to the zero very fast. When we have overdamped, then it goes faster to the zero, but now we have the oscillations here, so it is below zero and oscillate. And critically damped it is between this and this. It is goes to the zero as far as possible, but without oscillations. Okay, and characteristic equations. We know that characteristic equation is the denominator of transfer functions, and roots of these equations, which are poles of the network, determine the form of the network natural response. A convenient method for displaying the network poles and zero is graphical form, which use of pole zero plot on the complex or S plane, and zero are represented in this plane. Of course, it's only one possibility by O, and poles are represented by X. Okay, and so if the network poles are real or unequal, the response is slow, and therefore X from T takes a long time to reach zero. Okay, if the network poles are complex conjugated, the response is fast, but with oscillations. And the last case, the dividing line between the overdamped and underdamped case is the critically damped case, in which the roots are real and equal, and the response is quickly as possible, but with overshots. Okay, so now we can try to examine the effect of pole position in the S plane of the transit response such network. And when we calculate the voltage on the output, we can use the voltage divider here. So we know about the current. The current is the voltage by all the elements. So it is the denominator, and the denominator we have such value. And we know about characteristic equations for this, using the transfer functions, information from transfer functions theorem. And now we put some data, for example, 10 millihenries and 25 microfarads and some resistors. So we can try to examine this circuit using 5 value of resistance. So we know from when we see this one, when we compare this one and this one, we know about the natural omega of our circuit. So we can calculate that the omega zero is just equal omega zero square is equal 1 by LC. So we can calculate the omega zero and frequency. Okay, and from this one, from this part, we can calculate the zeta. And we know that 2 zeta omega is equal R by R. So we calculate the zeta, and we obtain the results for the zeta here. And now we can calculate the zeta for all value of resistors from 10 to 50 ohms. And now we calculate the roots of the denominators, S1 and S2. And when we calculate for all zeta, we obtain that from when we have the small value of resistors, we obtain a complex value from this. And for 40, ohms, we obtain just real part, and we obtain the first and the second is the same value as S1 and S2 is the same value. And when we further increase the resistors, we obtain only real value of the roots. Okay, and now we can draw this at this plane. So we have here the real part and imaginary part here, and now I put here the value from the previous, and I don't put value from 50 ohms, but it will be here and, for example, here. Okay, and so we have the RLC transient response for different zeta. So when we have the large value of resistors, we have such answer, such response, and when we decrease the resistor, we obtain the oscillation. And of course, the oscillations should be as bigger as possible when R is equal 0, because it is in this circuits connected with the resistance, impedance, and resistance and inductors and capacitors. The energy flows between capacitors and between inductors, and the resistor represents the such element when the energy is spread out. So the power is loose from this circuit by the resistors. Okay, and so when we have smaller resistors, this energy is transmitted between impedance and between reactance, but it takes a long time. Okay, so now I show you the simulation of this, and this is what I said previously. So in most applications, excessive overshoot is not desired. You must remember about this, and we can correct this using the damping ratio zeta. It is the damping ratio should be decreased, and which for this circuit, only for this circuit and maybe for similar, would require them increase the resistor value. And you will see the simulations, for example, for the R close to 0, because it is not possible when I use in the parametric simulations for R exactly equal 0. So we have oscillations for all time, and when we have the critical damped, we obtain the fast as possible to steady state, but without any oscillations. And of course, when we increase the value of resistors, we obtain longer response. Okay, and so I think it's the last one. The network with transfer functions, that's this formula, is Bibo stable. So Bibo is thinking bounded input, bounded output stable. Then and only when n is equal or bigger than m. So m is connected with the denominator, and it is the degree of denominator polynomial. And the second, all poles these transfer functions have real parts less than 0. So the all roots for the denominators are in the left part of S plane. And so in the other case, we have the oscillations, and this oscillations is difficult to predictable. And for example, of course, it is not connected only in the electric circuit, but maybe in the electric circuit is not such dangerous. But there is the case connected with Tacoma narrow bridge, and that collapsed in 1950 in the United States, and it is there was the mistakes from designing this bridge, and small wind for this for small specific wind for this makes such destroyed this bridge. So from we have wind as input, and input was bounded, but this construction is not stable. So from the bounded input we obtain not bounded output, and so it is the result. So dear students, thank you for this part of the lecture, and maybe we start about 20 past 11. I think the second lecture is very light, and maybe it not takes all time for this. Okay, so thank you. Okay, so welcome again. And now we are talking about something different. But as I said, it is a light topic connected with pulse waveforms and RC response. Maybe it's for several of you, it's obviously, and it is boring. It will be boring, but but it is also I think it is also we need it for example, for describe signals and using some definitions, some calculations. So it is more practical topic connected with scopes, with probes, etc. And okay, so let's go. I think it will be faster than previously, and it is a good idea to put some lighter lesson between too heavy, because in the next week we are talking about the Fourier transform. It is also a very important topic, but now we are focused on pulse waveforms and response. Okay, so first, okay. So I cannot say you that this lecture is based on the first book, Boylestad Inductor circuit analysis. So I think this book is much better for beginners, but the Irwin, which is the book, for example, for which I use for laplace transform. It is more concrete, more heavy. But for this book is lighter. It is the another point of view from topic or this topic. Okay, so this is based for inductor circuit analysis. Okay, so let's go. The learning goals: become familiar with specific terms and definitions connected with pulse waveforms, and I show you how we can calculate, for example, pulse wave, rise time, etc. How we can measure it in practice. Maybe sometimes it is automatically doing by, for example, by digital scope with these functions, but it is interesting knowing how it calculates. Okay, and be able to calculate the pulse repetition rate and the duty cycle of any pulse waveforms. Become aware of the parameters that define the response of RC networks, and understand how, I think it's the most interesting, how compensator probe of an oscilloscope is used to improve the appearance of output pulse waveform. Okay, and why pulse waveform, not sinus, cosinus, etc.? Because the pulse waveforms in our times, in nowadays, is commonly used, using for communication system, computers, radars, etc. So we control device by using these pulses and transmit data and information, etc. So you know about it. And so we have here the ideal pulse in this figure, and pulse width is TP, and pulse start from T1 to and finish to T2, and here we have the rising on leading edge. here, and here we have the furring on trailing edge at the end, and the high is of this pulse, ideal pulse, it is the amplitude. Okay, so the ideal pulse is applied in the analysis, the fundamental operation of device. You know about the ideal functions from the previous. Okay, but when we have the real circuits with capacitors and inductors, the slope is different. So I don't mean about the capacitors and inductors when we put with according to our intention to the circuit, but sometimes and in practice, of course, we have also the parasitic elements, parasitic capacitors, capacitance, parasitic inductance, which sometimes we cannot have any influence for it. Of course, we can, for example, change the designing of PCB or something to make control this, but in practice, we especially when we increase the frequency, we also expect that we have not ideal pulse, but such pulse like this. And so we have here the definition. What is the rising edge? Of course, when one signal goes to increase, and when signal decrease, it is the falling or trailing. And about the falling and trailing, that the falling edge always follows the leading edge. So it is such definition. Some it's more safe is using rising or falling edge. And you see at this picture, the pulse width is defined as a pulse width in the half of amplitude, because you notice that this is difficult to choose which point we should take to the analysis. So it is important. The most important from this picture is that we measure the pulse width in half of amplitude. Okay, and now I show you the results, simulations, very simple simulations. We have here the pulse source and two resistors, and after 1 millisecond, I connect to this circuit capacitors. Okay, so with any storage elements like capacitors, inductors, we expect the ideal pulse as a response, as an answer of our circuit. But with these elements, this response is not ideal. Okay, so we see from 0 up to 1 milliseconds, we obtain the amplitude 2.5 voltage at the end, and we have also the ideal pulse from this edge and from this edge, this slope. But when I put the capacitors here, we see that the amplitude for steady state is the same, but this time and this time is different. Okay, and so amplitude. What is the amplitude? Amplitude for most applications is defined as a peak-to-peak value. So the lowest and the highest point. But of course, if the waveforms starts and returns to 0, it is peak and peak and amplitude are the synonyms. So when we start at 0 and goes to the 0, amplitude is equal peak to peak value. Okay, and pulse wave or pulse the duration I told about it, and baseline. Baseline is the voltage level from which the pulse is initiated. So, for example, at this picture, we have here the voltage base at 1 volt, and the amplitude is equal 4. Okay. So there is the questions about the overshoot. I will talk about the overshoot also. And okay, so in this picture we have here the minus 4 voltage base and amplitude. Okay, and we have the positive going pulse. From positive going pulse means the base from increasing, and negative from base to negative direction. Increase to negative direction. Okay, and so now we can define the rise and fall time. So it is difficult to describe to find the moment when the pulse is start and when the pulse end. So the rise time on the fall time we measure as a time between 10 and 90% of amplitude. We cannot for these calculations we cannot take into account the overshoots, for example. Okay, and generally in our circuit TR is not equal to TF. And another definition is the tilt. Tilt is undesirable but common distortion normally occurring due to a poor low frequency response characteristic. It's called also the drop or sag. And tilt we can describe as a in the percent value of this or just a voltage, for example. And this one is the pre-shoot or overshoot distortion connected to high frequency effect of the system, because I said we have the parasitic elements. For example, when we make a PCB, we have the parasitic capacitors between, for example, our the ground layer and our signal, and for the same is for induction, but sometimes we have also the parasitic induction and capacitance in cable, and so it is when we obtain in practice the ringing. So we have here the overshoot, and so before is the pre-shoot for this. Okay, and ringing. Ringing is the interaction between capacitance and inductance, as I said, and so we have the overshoot, which is from this baseline up to and this point, and ringing is the periodical signal here. So elements network their natural or resonant frequency. So it is when the energy is flows from capacitor to inductance, etc. Okay, so it is connected with ringing. It is connected with parasitic resonance circuits. Okay, and example here we have the picture, and now we can determine the following for the pulse waveform positive or negative going. So I think it's positive going. Baseline, you see it is the 0 voltage. Tilt is also 0. We see here. And amplitude. So amplitude is from the 0 up to here. We know about this is the picture from the scope. And vertical sensitivity, we have 10 millivolts per diff. So we have the here 1, 2, 3, and 4. So the amplitude is 40 millivolts, and TP we can measure here, and 1, 2, about 3, less than 3, and if okay, we calculate by multiplication this one, and 3. It's close to the 15. And T rise and T4, it's about from up to now, and to one small part, it is 1 microsecond. It is equal to 2 microns, and 2 we have 1, 2, 3, 4. So it's 20 microsecond is TF. And so we have here the answers. Answers for the not so I make the mistakes because it's the biggest 5 microseconds. So it's 4 and 2. Okay, and other, so pulse train. It is the series, series of pulses. The pulses may contain informations. For example, as we see, I show you the information which is called in P pulse wave modulations, for example. And periodic pulse train, it is the pulse train which is repeated with period t. So we have here the period between the elements, which is the repeat. And period of pulse train, the time differential between any two similar points of pulse train. So, for example, when we have the one period here, and when we find the similar point, this is the period, the distance between two similar points, the same point in the pulse train. Okay, and pulse repetition or pulse repetition rate is defined by 1 by period, and you must notice that the shape of periodic pulse does not affect the determination of the pulse repetition frequency. Okay, and more interesting, duty cycle is the factor which shows the pulse duration compared to the period. And for example, we have here 2 pulses, first and the second pulse. And here the time width is equal 0.25 microseconds, and here is the width is half millisecond. And so duty cycle in this case is equal 25%, and in this this is the 50%. Okay, and so determine the pulse repetition rate and duty cycle for trigger waveform. Okay, so we have the diff for this one, and we know the sensitivity from this point to this point. We have 10 microsecond, and so we can calculate the period. So we have 1, 2, and 2, and we have the 3, 5 from this one. So we can obtain that this result is 26 microseconds. Now we can calculate the frequency for that, and also time connected with the width of this path. And duty cycle, when we know the duty cycle and when we know the period, we can calculate the duty cycle of such signal. And average value can be determined by two methods. From definition, definition is valid for all waveforms. It is just we can use the integration. We can integrate signal in one period and just divide by this period. Of course, the scopes use the calculations in the digital domain, and term specially related to pulse waveforms, duty cycle in decimal forms, not in the percent. So we have the average value as duty cycle multiplication by peak value plus 1 minus duty cycle multiplied by baseline value. And so we have here the example determine the average value for periodic path. And firstly, we can use the definitions for this. So we know that when we use the integration, we find the area of this signal, and you know that the t is equal 10 microsecond, and here we can try to calculate this this rectangle area of this rectangular. So we have here this factor, and this factor is connected with this rest of the passes. So we have here the 6 milliwatt and time is equal 4 microseconds. As a result, we obtain 4.4 milliwatts. And now, from the second method, duty cycle multiplication by peak value. Peak value, we have here 8 milliwatts, and duty cycle, it is 4/10, and also we calculate the second form, 1 minus duty cycle multiplication by baseline, and as a result we obtain the same value. Okay, and now the more practical questions: how we can measure the average value of the signal without such function in the scope. Because in this time, I can guess that you all of you use only the digital scopes. I don't suppose that you use, for example, in metrology the analog scopes, but previously. Before the digital scopes, we have only the analog scopes. In the analog scopes, we use, instead of LCD display, we use the lamp, scope lamp, and scope lamp. It is a lamp when the electrons illuminator on the front of this lamp, and we use the electrical field for change the change the point when the electron lights the illuminator. In this, but it is another type of display. But also it was impossible to calculate some informations like RMS value or amplitude, etc. So we just use the screen with the grid, and we must calculate from this grid. We cannot use, for example, cursors for such scope, and so we cannot use such functions how like average amplitude. So how we can measure without this function? Maybe you noticed that in the scope we have two types of coupling. We can couple our signal to the scope by DC or AC way. So DC is the direct current, so we just connect directly to our signal to the scope. But there is also the switch when we connect our signal to the scope by the capacitor. So of course you know that the capacitor is the brake for the DC voltage or current or DC signals. So it blocks it. Okay, and what is about circuit when we connect firstly signal with coupling, DC coupling and AC coupling. Okay, so you see that the red one is using the DC coupling, and signal is going from 0 to the to 2 voltage. And for the now I switch I move the switch to the another position, the coupling AC, and now we have the same amplitude here, but the baseline is going down. So we cannot hear the 0, and we have the minus 0.6 volt. Okay, and the difference is from this reason that the average value of this signal is blocked by capacitor. So when I measure the peak value using the DC coupling and after the AC coupling, I can calculate by average value as a peak value DC minus peak value AC. Okay, and of course, maybe you think that this function it was using only in the old scopes because people want to calculate AC average value of signals. Not only because this functionality is not connected by peak value. This is by a way, but the mean function of switch AC and DC is connected with something else. I show you maybe this. We return to the another. Okay, so we see here. Okay, so sometimes we can observe the signals with small average value and small ringing. For example, so ringing and something for us now is something interesting, which is only in this region, not for all signal, but only in this region. So without this function, without AC functions, we cannot see this because we cannot use. Of course, we have also in the scope the offset. Regulation of the offset, but sometimes it is not enough because the signal is too high. And for example, when we want to observe this noise, it is not possible without using the AC. But when I cancel the average value, when I cancel this value, I can observe only this, and it is the reason why we use the AC in the scope. Okay, so now we know such a system, of course, and we can determine the output voltage in this system. Okay, we know the Laplace transformation, so it's not difficult, I think now. So we know about the voltage at the time when we start the analysis. So we have the voltage, final voltage and initial voltage here, and the part connected with this resistance and capacitors. And of course, we can calculate that the voltage is on this is the initial value plus current, which is flow, and in this and multiplication by 1 by SC. Okay, and of course it is not good form for the change to the time domain, and so we make some calculations, and for us it is not good idea to use here the multiplications, and we change to the partial value this part of our equations. So we use Q1 and Q2, and now when I calculate this one, we obtain the equation which describes the voltage at the capacitor. So what we see here? We see here the voltage connected with the source and initial value, and this knowing element. Okay, and we can also calculate the current in this circuit. We know that now we know voltage at this point, so current it is just voltage from this, and minus this voltage, and divide by R. And we have also the equations for the current, and we know that this is the amplitude of the current. So we have this the I max. Okay, and now we examine it. We can draw this function. We have here the initial value and the final value, and final value is connected, of course, with the source value in this circuit, and the voltage F is the steady state resting value of voltage across the capacitor when the transient phase has ended. Okay, but when? When? The question is when. Because of course in theory the time is after time equal infinity. The voltage across the capacitor will reach the same value, but the transient period for this, in practice we can assume that after 5 tau where tau is the time constant of the network, we obtain this steady state. Okay, and from in this network, the tau is equal RC, and when we can calculate the error steady state approximation by using with this assumption t equal 5 tau. For it is maybe simpler when you use initial voltage equal 0. So we use this formula for that, and we can calculate this error from this. So here we have the voltage after time equal 5 tau. So I substitute this value in this place, and minus this voltage from steady state, and I divide by this. So when we use such approximations, the error is only 0.68%, and very often in practice we can use tau equal 3 RC for a steady state, for describe the steady state, and for this value for 3 tau, error is about 5%. So you can meet in practice this value or this value. Okay, and now we can we should sketch VC for step input. Assume that we have firstly minus 4 milliwatts, and some signal at the input is changed from minus 4 to the 10 milliwatt, and here we have the circuit, and determine when we obtain the zero voltage across the capacitor. If the step changes level at t equal 0. So some information about it is the initial value and final value, and now we can calculate also the tau value. We know the resistance and capacitors from this one, and so we can calculate the voltage across the capacitor from this. Just substitute for the previous equations, and now we make some calculations to obtain the time value for the voltage equal 0. So now we have the voltage equal 0, so we put here the 0, and when we put 0, we can move this one for the another, and when we make some calculations, we obtain time 3.37 microseconds. After this time, we have voltage equal 0 from minus 4 to milliwatts to 0. So after this time, we have exactly 0 volts, and so it is would see in this picture. So it is the initial value and it is the final value, and here we have this point. Okay, and now we have the square wave with 15 duty cycle, and the average voltage equals 0 volts. So it is a particular form of pulse waveform. We can of course calculate duty cycle and average value for this, and when we the application of DC voltage in series. So when we want to increase or decrease the base value, we just put in DC voltage in series. For example, here you can see that the amplitude is equal 1 volt and the offset is I add here the 1 volt source. And on the results, I obtain such functions that this starts from 0 and to the 2 voltage. Okay, and now we apply it to this signal to RC presented above. Okay, so the period of square wave can have a pronounced effect of the resulting waveform for VC. For the analysis to follow, we assign the steady state condition established for a period of 5 time constant. And when we take this to account, we can examine three cases. Okay, and first is when half of period is more than 5 tau, and the second is exactly, and the last one is less than 5 tau. So now we can see what is happening. Okay, and firstly we have the time. This first case when half of period is more than 5 tau, and so we can observe that the shape of output voltage is similar to applied voltage, and this current consists of series of very sharp spikes. So it is only in this, and when the current is flow just only when we change the amplitude of the input signal, and during the trailing edge VC reaches a zero value. And direction of discharge current is an opposite to changing phase. So we see this, and we also see that in this phase we obtain the 0 value for some time. Okay, when we have the another cases, we obtain such signals. Of course, it is very similar, but this part of the signal is disappeared in this case. So this is the case between the first and the second. So we have the VC, which is its final value just before beginning a discharge phase. So just after this we obtain this value, and now it is the discharge phase and charge phase and discharge charge of capacitors. And here we have the very similar situation with the current. The current goes to the 0, and after just after goes to the 0, goes to the down, and goes to the 0 and goes to the maximum value, plus maximum value, etc., etc. So in this case, VC is not longer similar to square wave input, and it seems like a triangular waveform. Of course, it is not the ideal triangular waveform, because it is not linear slope here and here, but it seems more triangular than square. Okay, and we have the last one, when the half period is less than 5 tau. And we have this, in this situation, we have such that after this time we don't have the maximum value of voltage. So we cannot see the voltage from the source at the output after this time, and because now it's discharge phase, and after this discharge phase, which is shorter than the 5 tau, we also don't obtain the zero value, and now it is the charge, discharge, charge, and discharge, etc., etc. So the voltage will not reach the final value, and in the most instances, it is a good approximation to assume that steady state, the steady states for this case is established in 5 cycles of applied voltage. So you can see also the current. The current here is not equal zero just before moment of the switching. And in this situation, but after steady state, we obtain this that we have this value and this value from the absolute point of view. It is the same. It's only the sign is different. Okay, and here we have the such cycle, and we have the four different constant, 4 different tau time constant for this one, and in this magenta line it is the source, and we see, for example, when the time constant is bigger, we obtain this time is also longer for assume the steady state. Okay, and when the frequency increases, there will be a flattening of response VC, and so you can see at this picture that from 0 up to 5 milliseconds, the source 1 was applied for this circuit, and we see this one, and this voltage, but the changes in amplitude are big in this case. It is about one voltage. But when I increase the frequency, so I change the variation between tau and frequency, we obtain the smaller changes for this. And you must remember that this simple circuit, it is the low pass filter. It is the low pass filter, or just integrator. It's called also the integrator. And when we remind the definition of average value, we know that in this we have integration. So after integration, we obtain the average value of signal. Okay, and so the information under steady state conditions, the average value of VC will be equal the average value of applied square wave. Okay, and now we can try to sketch the VC and IC signal for this circuit. We have here the frequency of this and amplitude. Okay, now we can try to calculate the period from this and half of period, and also we can calculate the tau knowing the value of these elements. and the pulse width is exactly equal to time constant of the network. So the value of VC will not reach the final value before the first pulse to square wave input returns to 0 voltage. Okay, and we can calculate the voltage value from 0 time to half period, and we know the voltage value is equal 0 here, and final value is 10 milliwatts. So we apply for this knowing equations, and after one tau, it is also the characteristic value. After one time, we obtain 63 and 2.2% of the amplitude. So in this case, we have 6.32 milliwatts. Okay, and now I sketch all these signals. So now we calculate amplitude in this case. Now we try to calculate for this region from t half t to 1t. So this is the discharge phase between this time and this time, and so now we should switch the initial and final value, because for us the final value from the previous is the initial, and we assume that we have here the zero voltage here, and we can calculate the voltage at this point t. And when we're using these equations, we obtain the value, but in this case we can use, instead of t equal t, only t2. We can substitute for this, okay? Because we only examine the time in this region. And from them, when we use for this, we obtain the value in this at this point as a 2.32 value. And we, of course, we can make this for all these signals after. So we can see here for 5. Near the 5t. So the waveform has essentially reached steady state conditions if in a period of time less than 5 tau. Because the changes are here here we obtain the same value. So we can see here and here we have the same value, and so the average of this value we can use in this and divide by 2, sum of this and this, and obtain the just average value of this signal. So this is the circuit for obtain the average value. Okay, so knowing the VC, we can calculate the current, and this is from the current. The current, of course, is the largest at the beginning, because capacitor is uncharged, and so we cannot see the symmetry here. And after some time, after in the steady state, we see the symmetry here, and we see that we have the same value here and the same value here. Okay. Of course, the average value is equal 0, because in the steady state, we know that the capacitor is the brake for this for DC. Okay, now it is the application of this. Maybe you see the oscilloscope attenuator, and maybe you use it in the practice, for example, in the laboratory in previous semester. So sometimes when we measure the signal using the scopes in almost always we use the probes for this. Of course, it is possible to use cable instead of the probes, but as I said, almost we used always we use the probes. This is a convenient method for examining, for example, voltage on the PCB or etc. Okay, and but the maximum amplitude which we can measure by scope is limited. For example, is limited for 20, maybe 50 volts. It is the maximum peak-to-peak value for the common using scopes, for typical scopes. But when we want to reduce the magnitude of input voltage, we can use the small switch, which is on the probe. Maybe you see it is the switch when we can change this factor. And sometimes it is writing here x1 and x2. So x1 it means that our signal is going to the scope, and x10 it means that attenuator probe it's divide our input signal, and we obtain on the input on the scope smallest 10 smaller signal. And okay, so it is obviously that we can use a resistor divider for reduce the amplitude. And we see the scope, for example, we have here we can see here the resistance. It is the internal resistance of the scope, and it is commonly used to. We have one mega ohms. Of course, it's not obviously, because for oscilloscope with high band, for example, several gigahertz, sometimes using another front end with for example 50 ohms. But for the typical scope, we have just one mega ohms internal resistance. Okay, so when we use the outside 9 mega ohms, we obtain the voltage divider. Of course, we cannot use 10 mega ohms. It seems more practicable, but when we calculate from voltage divider, we obtain. This is the internal resistance, and we have because we have sum of resistance in the denominator, we can use this one, not 10 megahertz. So it is simple, and we expect that it's good. It is a good idea to make such probe with such attenuator. But it's in practice it is not simple, because we have some additional parasitic capacitors. For example, the parasitic capacitance is it's from the cable, and also in the scope we have the parasitic capacitance, and more producers gives information about this on the scope, and you can see near the input that we have the about the internal resistance and internal capacitance. Okay, so we can change this schematic into the electrical schematic only, and so we have the resistance of the which we put in the probe, 9 megaohms, and here we have the capacitors, internal plus cable, and so it is the V scope. Okay, and now we can apply it for this such signal, square signal, and it is good idea to use Thevenin method for this equivalent of the circuit. So I cut here this circuit, and from this point I calculate the Thevenin voltage and resistance, and this circuit I can show using the Thevenin method like this one. So we have here the voltage, resistance, and capacitors here. Okay, and now we can calculate the time constants for this. We obtain 27 microseconds. And so now I show you the results of simulations for only for 5 kilohertz. So I applied the signal on the input 5 kilohertz and make the simulations. Okay, and so we can also try to calculate the period, and period is 100 microseconds, and you can see that the period is smaller than 5 tau. Okay, and okay, so such probe produce a serving rounding distortion of square wave and poor representation of applied signal. So we can expect that this probe is not a good idea using this probe. And this is the simulation, and you see that we have here the only 5 kilohertz signal with such amplitude, and just I put these resistors and these capacitors. Okay, but we know, and I said you that we have the scopes which works up to several or tens, maybe even hundreds of gigahertz frequency, but so we have only the 5 kilohertz, and we have such distortion here. So it's not why we can omit it. Yeah, why we can help for this probe. Okay, so in practical, we cannot use only the resistor here. In practical, to improve matters, a variable capacitor is added to parallel with the resistance of the attenuator, resulting in a compensated attenuator probe. what it means that the probe is compensate. So we can examine such schematic. So this is the voltage of the scope. We have the input voltage, and this is the impedance, this part of the circuit, and we have also the impedance, this part of the circuit. And when we put off, we know that the equivalent of this circuit, Zs is equal here. So I calculated it because it is a parallel connection for this, and the same we obtain for Zp here. Okay, and when we substitute this value to the main equations, we obtain such value that this is the V scope is equal V input and these equations. But you can see this. So it is more complicated by previously, but when we choose good capacitor's value for Cp, we obtain the same time constants for this one and this one. And for in this situation, when we obtain the same value, we can omit this one, and this one from the equations. So from these situations, we obtain pure resistance character of our divider. But we should add the capacitor for this, and to obtain the equal time constants for this and this part. Okay, and so it is for this one we obtain pure resistance character, and now, as you can see, the scope is now insensitive to frequency. Previously, it was sensitivity because you can put, for example, in these equations, please notice that when we put Cp equal 0, we obtain sensitivity for the frequency, because we cannot remove in this case j omega from this, and the omega of course represents the frequency of our signal. Okay, and but what is in the what we can do in practice, because so you expect that we have here, okay, so we have here the resistance 1 mega ohm, and we have here 30 picofarads. So when we increase the resistance to obtain the same time constants, the Cp should be 9 times lower. So it is about 3 picofarads. It is very difficult to measure such capacitance. So in practice, it is not good idea to measure and solve to such capacitors to our probe. So instead of this, we use the variable capacitors, but it is not good idea to measure this capacitance. In practice, we have another simple method, and the most using scopes. I show you the scope which we used in our laboratory. This is the scopes from laboratory. In most of scopes has some internal generator, and So we see here such connectors. The first is the connectors with the grounds, and second is the signal. Yeah, and producer writing probe compensators, and we have signal 5 voltage, amplitude, and 1 kilohertz. So in laboratory, we can simply adjust the probe capacitance using a standard or knowing square wave signals until the desired sharp corners of the square wave are obtained. So when we have three cases: under compensation, current compensation, and over compensation. It's similar situation to damping factor, and it's connected with damping factor, of course. And so we connect this in practice. We connect this probe to the scope, and we observed the results on the scope. And when we have a correct compensation, we obtain such like this blue signals. And over compensation and under compensation, we see respectively such green or red signals. And this is the point for compensation. We use such tool for move this screw and obtain the correct compensation. So in practice, it is simpler than in the theory. Okay, and another informations connected with the scope. Maybe this information it will be useful for the future, for when laboratory will be open. Is that the common point G and D is common in the scope. So when we use two probes for measuring the ground is with this. It is the cable with the crocodile. The ground must be connected to the same point of the circuit, to the point with the same potential, with the same voltage. We cannot connect first crocodile here and, for example, exchange this probe with the crocodile, because we just short the output to the GND. So it is very important when we use two probes for measuring. Okay, and at the end, I would like to show you some RC network in practice. It is trigger system for monostable flip-flop device. You examine such device on the laboratory, on electronic circuit laboratory in fourth semester, and this is the part of such device. It is only the trigger system, and so we have here the source. We have here the source, and we have the capacitors, resistance 1 and 2, transistors, and diode here. So firstly, I draw the signals from the source. It is the pure square signal. And after this capacitors and this resistor, it is the differentiation device. So we after this this device we we see only the spikes here, and the pulse go up and go down. And of course, these pulses should be symmetric, but it is not symmetrical in this system because we have here the diode, and from the diode short these pulses, and we see only the voltage which is typically across the diode which is on. This is the Schottky diode, so we have only the 0.4 voltage here, and this diode is for saving the transistor. For previous damage this transistor by voltage less than 0, and this resistor is only to limit for the current for this transistor. On the end, the transistor is on when its signal is go up. So at the end we obtain such pulses. So this is the quite useful trigger system for flip-flops, for example. So we convert this square wave to some spikes, and very sharp. Okay, and now pulse wave modulation in the practice. So I told you about at the beginning about this. So we have here a generator. It is very simple generator 555, and it generates a square wave, and the square wave is modulated with this source. It is the 1 kilohertz source, and so we first we see the carrier signal. It is the carrier signal generated by this generator, and now this is the modulating signal, and after that on the output we see the modulated signal. So it is connected with the amplitude at the special moments. So, for example, these pulses I connected for this low amplitude, for amplitude equals 0, and the wave is larger for higher amplitude of modulating signal. So this signal consists information about amplitude, about the voltage of modulated signals. For example, we can imagine that the modulated signal is my signal, for example, from microphone, and I must transmit to the receiver, and so we have such signal, and using simple low pass filter, I can from this modulated PWM modulated signal we can obtain the original information from this. Of course, it is not exactly the same, but it is very similar, and it is in practice use. So I see the one question about compensation, we can compensation, how often we can compensate. We can check this probe, and I think, of course, when we have it's connected with our research, but so in practice we can do it, for example, for several years. It is good, but we see that it is not good signal for in practice when we use the scope, and then we should make this compensation. But of course, in the laboratory, in our laboratory there is the person who is responsible for this one, and I know that students cannot use this and make some changes on only these men is responsible for this. Okay, so it was the last one. So thank you for your attention today, and have a nice weekend. So see you.